We are now going to take a look at an incredibly powerful mathematical tool, the Taylor and Maclaurin series. Here we'll relate them to some ideas that we've seen before, and we'll take a look at how they might be useful to us. Let's consider an idea we've seen previously, the nth order Taylor polynomial centered at some x value equal to a. We're going to use this polynomial, which is the sum from k equals 0 to n of the kth derivative of f evaluated at our center a, divided by k factorial, times x minus a to the k, to approximate f of x for values of x that are near the center. Remember that as we let n get larger and larger, our approximations got more and more accurate. Recall also the idea of a power series, the sum from n equals 0 to infinity of c sub n times x minus a to the n, where c sub n are the coefficients and a is the center of the power series. We've seen that we can use power series like these to rewrite functions. F of x equals 1 over 1 minus x is a good example. Taylor and Maclaurin series expand this idea and allow us to look at whether or not we can write some other complicated functions as infinite series, and if so, for what values those series are exactly equal to the function. In other words, Taylor and Maclaurin series allow us to examine the question, what happens as n goes to infinity? If f can be approximated using a finite Taylor polynomial, is it then the case that f of x can be exactly equal to the infinite sum of the kth derivative of f evaluated at a over k factorial times x minus a to the k? This infinite power series is called the Taylor series. Note that if we choose our center at 0, the series is then called a Maclaurin series. Now that we have a working definition for the Taylor series, we're going to examine when such series might converge, and also when the series might be exactly equal to the function that we use to construct it. A Taylor series cannot be equal to a function value if it doesn't converge. So our first order of business is answering the question, where does the Taylor series converge? Just like we did for power series, we will use the ratio test to determine the interval of convergence. Once we know where our series converges, we can then examine for which of those values does the series actually equal the function. It turns out that this question depends entirely on the notion of the remainder that we explored when we looked at Taylor polynomials. Recall that we can write our function as the sum of the nth Taylor polynomial and some remainder r sub n of x. And we know that r sub n of x is exactly equal to the n plus first derivative of f evaluated at some point c divided by n plus 1 factorial times x minus a to the n plus 1, where c is some value that falls between our given x value and our center a. For any given x value, in order for the function value to be equal to the Taylor series, we need those remainders to get smaller and smaller. In other words, f of x is going to equal its Taylor series if the limit as n goes to infinity of r sub n evaluated at x is equal to 0. So now we have the tools to build a Taylor series, figure out where it converges, and then establish where on its interval of convergence the Taylor series and the function are exactly equal to one another. Let's use what we've learned in an effort to build the Maclaurin series for f of x equals cosine of x. Then we'll find that interval of convergence, and lastly we'll figure out for which x in that interval the series actually converges to the value of the cosine. So our function is cosine of x. Our center, because it's a Maclaurin series, is 0. So let's start by building a list of coefficients and see if we can establish a pattern in order to write our series down. So I'm going to make a list here of my n value, my nth derivative at 0, and then my nth coefficient. And we'll do this for a few n values until we start to establish a pattern. So when n is 0, the first derivative is, or the 0th derivative is just the function itself. So this is going to be the cosine of x. and that cosine of 0 is 1. So our very first term is going to be the number 1. When n is 1, our first derivative is negative sine x. That evaluated at 0 is 0. So the coefficient of the term c sub 1, or the c sub 1 coefficient, is 0. When n is 2, we take the second derivative. The derivative of negative sine of x is negative cosine of x. The negative cosine of 0 is negative 1. So our next coefficient is negative 1 over 2 factorial, which is, of course, just negative 1/2. For our third term, the derivative of negative cosine is positive sine of x. Of course, the sine of 0 is 0, so that term drops out. We can already start to see a pattern here with our odd terms dropping out and our even terms sticking around. We'll do a few more to see if that pattern continues. For n equals 4, our fourth derivative is going to be cosine of x. The cosine of 0 is 1, and we can see our pattern is going to start to repeat now. So our coefficient here is not 1, but 1 over 4 factorial, which is going to be 1 over 4 times 3 times 2 is 24. Okay, so we have a couple of things going on. First of all, we notice that every term that has an odd n value is 0. We can also see that each term that isn't 0, the denominator is going to be n factorial. And we also see that this is alternating. All right, so somehow we have to condense this now into a series where we skip every other term. So if we're going to write this as the sum from n equals 0 to infinity, what we're going to do is we're going to write this as negative 1 to the n. That's going to give us the alternating positive, negative, positive, negative. Then we can see that we're going to take 2n factorial. That will allow us to skip things like 1 factorial and 3 factorial. And then we're going to raise x to the 2n power. Again, because when n is an odd number, the coefficient is 0 and the term drops out. So we'll keep everything even by multiplying all of our n values by 2. Now that we've established the series, we're going to go ahead and try to find its interval of convergence. For this, we use the ratio test. So we're going to look at the limit as n goes to infinity of the absolute value of the n plus first term, which will be negative 1 to the n plus 1, times x to the 2 times n plus 1, all over 2 times n plus 1 factorial times 2n factorial over negative 1 to the n times x to the 2n. If we tidy that up a little bit, first of all, the absolute values allow us to, in some sense, ignore the negative 1 terms because they're going to become positive. So we can just think of this now as x to the 2n plus 2 over x to the 2n times 2n factorial over 2n plus 2 factorial. That gives us the limit as n goes to infinity of the absolute value of x squared times 1 over 2n plus 2 times 2n plus 1, using the fact that 2n plus 2 factorial is 2n plus 2 times 2n plus 1 times 2n factorial. Well, if we take that limit as n goes to infinity, we get 0. That is less than 1 regardless of x, which tells us that our radius of convergence is infinity and our interval of convergence is negative infinity to infinity. All right, the last piece of our puzzle is to figure out now is it the case that for every value, every real number in our interval, which is in this case every real number, is the value of the cosine of x actually equal to the Taylor series? So what we have to do is now figure out an expression for our remainder. We know that r sub n of x is, the definition of it is the n plus first derivative evaluated at some value of c, all over n plus 1 factorial, times x minus a to the n, but in this case that's just x to the n, because a is equal to 0. Well, we know that we can bound this. We know that the absolute value of r sub n of x is then less than or equal to 1 over n plus 1 factorial times the absolute value of x to the n, because f to the n plus 1, the n plus first derivative, is always less than or equal to 1, because the n plus first derivative is either cosine, sine, or the negative version of each of those. So that is always less than or equal to 1. So if we take then the limit as n goes to infinity of the remainders, that's going to be less than or equal to the limit as n goes to infinity of x to the n over n plus 1 factorial. We can put some absolute value bars on that. But if you recall, this is going to be equal to 0. We know that x to the n grows more slowly. We've seen this in a previous theorem than n factorial, which means that that limit is equal to 0, which means then that for all x belonging to our interval negative infinity to infinity, the cosine of x is exactly equal to the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n all over 2n factorial. So we have found a way to express the cosine of any angle that we want in terms of a polynomial. It's going to be the case that most of the Taylor and Maclaurin series that we work with are exactly equal to their functions over their entire interval of convergence. This is exactly what makes them useful for us. However, there are some exceptions to this, and they're kind of fun to think about. So let's take a look at one of these. The animation below shows the function f of x equals e to the negative 1 over x squared for x not equal to 0, and 0 for x equal to 0, along with several of its derivatives. If you focus your attention at the origin, you'll notice that all of the derivatives are 0 at 0. Well, the math's a little more complicated than I want to get into right now. It is the case that for this function, all of its derivatives exist, and they're all defined at 0, and they're all equal to 0 at 0. Let's use this fact to construct the Maclaurin series centered at 0 for this function. Since the definition of our Maclaurin series is going to be the sum from n equals 0 to infinity of f to the n of a over n factorial times x to the n, given that f to the n of 0 is equal to 0 for all n, this becomes the sum from n equals 0 to infinity of 0. Well, that clearly converges everywhere. That's going to converge for all x. So its interval of convergence is negative infinity to infinity. However, if x is not equal to 0, then f of x is e to the negative 1 over x squared, which is not 0. So what we see is that we have a series that, except for x equals 0, the series is never ever equal to the value of the function. Okay, so what we know is that if we define the Taylor series as the sum from k equals 0 to infinity of the kth derivative of a function f at a divided by k factorial times x minus a to the k, where a is what we call the center of that series. And we use the ratio test to determine the interval of convergence, then the function is going to be equal to that series for every value in the interval where the limit of the remainders is equal to 0.